Okay, then. Okay. So the lecture is still in chapter 2. Okay, chapter 2. All right. So you can read the textbook, the ebook I've given to you. Okay. Actually, you have to buy this book. Okay. During the normal semester, you need to buy the book. So that is the suggested reference book because the syllabus is built on that particular book. Okay. All right. So if you look through here, okay, so this is the chapter that we need to do. Okay. Today we're going to start with the calculation. So the last lecture is regarding to the how you develop the equilibrium diagram. So I did ask you to maybe some of you have done that exercises already. Okay. So bear in your mind if you were to plot the equilibrium diagram, because equilibrium diagram will be used in this course. Okay. So if you were to plot the equilibrium diagram, you should plot for x-axis, the maximum value is 1. Okay. For y-axis, the maximum value is also 1. Okay. So normally, if I were to give you some comments regarding to what you have, maybe you have practiced before, okay, all right. So the x-axis is normally starting from the beginning of the box, from your graph paper towards the end of the box, okay, of your graph paper, okay. And the y-axis is normally double the length of the x-axis. Okay, so normally, but you have to begin at the beginning of the boxes, at the beginning of the boxes of the graph paper. Okay, so that you can get a very good graph. Okay, why do I say that? Okay, why do I say that? The reason is because, okay, if you produce a graph which is very small, okay, or maybe smaller than what I want you to have, okay, your answer will be a little bit different than my answer, or your answer can be quite far from the scheme answer that is provided for the assessment. Okay, so that will lead you to the wrong answer. Okay, because the difference are very big. Okay, so I suggest you to make sure that you use the whole length of your x-axis from the your graph paper, and then double, maybe double the length of your y-axis. Okay. All right. So you are expected to calculate the mole fraction of the liquid, and the mole fraction of the vapor. Okay, you are expected to know how to calculate the mole fraction of liquid and mole fraction of the vapor using the Rod's law and Dalton's law. Okay, and then at the same time, we have covered the method how to calculate the relative volatility of the mixture. So this alpha is used, the value of alpha is used for you to make decision whether your decision is correct or wrong, or whether your decision is good or bad. Okay, so by looking at the value of alpha, so this alpha is the forecasting value for you to make a future decision whether to use a distillation process or not for the given mixture. Okay, so you can use this formula that shown here, and how you develop this formula, you can refer to your reference book that I've given you in the form of ebook. Okay, all right, so some exercises have been done. Okay, Now let's proceed to the distillation. Distillation. All right. So there are many types of distillation column that you're going to learn in this course. Okay. The most popular distillation column that we're going to do in this course is about the fractional or continuous distillation column, or maybe rectification. Okay. And the basic one that we have is flash distillation column. Flash distillation column. We also have batch distillation column. Okay, we also have batch distillation column, but that one we will cover later. Okay, because we need to go fast for your calculation method first. Okay. All right, so this is the schematic diagram of the flash or equilibrium distillation process that you're going to have. Okay, so we are going to start to do the calculation on the mass balance. Okay, so let's make it bigger. Okay. All right, flash distillation column. We only have a single stage for this column. Single stage. Okay, single stage here. All right. So this is where the liquid mixture that we're going to have will be separated. Okay, will be separated. All right. And then the liquid mixture is partially vaporized. Okay? Partially vaporized. So you're going to feed, okay, you're going to feed the mixture, all right, the mixture that you have. So remember that for this topic, we only deal with binary mixture, two components only, all right, two components, all right. And then that two components should be able to be separated using distillation column, okay. So this is one type. Okay, flash or equilibrium distillation. Okay, now the vapor is allowed to come to equilibrium with liquid. Okay, then the vapor and liquid phase are separated. So what you can see here is actually whatever product that you get, okay, on the top of the column and at the bottom of the column, okay, they will be in equilibrium to each other. Okay, so what we can see here, the vapor component that we have on the top of the column and the liquid component that we have at the bottom of the column will always at equilibrium state. Okay, at equilibrium state. Okay, so this is a simple schematic diagram that you're going to have. So whatever feed that you have, okay, we're going to use symbol F for the feed, all right, and then the feed consists of A and B. Okay, because you have two components, all right? So you're going to present that as A and B, all right? Now, so in this case, to make sure that we have easily solved the problem, because you're dealing with two components, all right? It means that you have about two unknowns, okay? Two unknowns, A and B, okay? For two unknowns, all right? To solve the two unknowns, normally you need at least two equations, okay? At least two equations, all right? So if you know one of the unknowns, all right? If you know one of the unknowns, okay? So you can solve the other unknowns, right? So what you have is actually the symbol that you have here, okay, for XF represent the more volatile component, okay? The more volatile component. So the more volatile component represent the light component, the light component, okay? And that light component is easy to vaporize. The light component is easy to vaporize. So you're always going to represent, okay, component A to be the lighter component, which is easy to be vaporized. Okay, will be easy to vaporize. So if you can see in other way, okay, the light component, which is easy to vaporize, will have lower boiling point. Okay, will have lower boiling point compared to the heavy components. Okay, which is little bit difficult to be vaporized. All right. So what you're going to have here when you talk about distillation, the light component, okay, will be collected, okay, will be collected at the top of your column. Okay, at the top of your column, since it is easy to vaporize, okay, it will vaporize first before the heavy component vaporize. So we have to make sure that when we want to heat the mixture, we have to look at the boiling point. Okay, we cannot have a temperature or operating temperature which is near to the boiling point of heavy component. Okay, why? Because if it is near to the boiling point of the heavy component, both will be vaporized at the same time. A also vaporized, B also vaporized at the same time, and will be collected at the top of the column. But if both are collected at the top of the column, majority of them are collected at the top of the column, there's no use of separating that mixture. Okay? No use, because you still have the original components, original purity of the components that you have. So what we need to do is to make sure that when we heat the mixture, we have to mix the mixture at the temperature very near to the temperature of very near to the boiling temperature of the light components. Okay, if you want to go further a little bit, it also can. Okay, so definitely some of the heavy component will also be vaporized too, but not as much as the original components. Not the original, no, not majority of component B will be vaporized. Okay, so you're going to have purity which is maybe about 90%. Okay, consists of A component at the top, maybe 10% of B component at the top. Okay, so we would like to achieve some purity, because the purpose of doing distillation is to make sure that you can separate both mixture from each other. Okay, all right. So as I have mentioned to you, when you talk about distillation process, the process involves heat energy. Okay, so that's why you need to heat the feed. Okay, you need to heat the feed, right? So we're going to represent, okay, we're going to present the symbol here. F for the feed, V is for the vapor, L is for the liquid, because the heavy component, okay, will be separated in the liquid form. Okay, all right. Now, the XF here represent the component A. Okay, XF here represent the component A. You can put the subscript as XFA. Okay, XFA. So since we are referring to A only here, therefore the Y star here will represent Y star for A component. Yeah? And X star here represent X star for A component. All right. So if you know the X star for A, okay, you know XA, you should know your XB here in this case. Okay, because you only have two mixture using the mole fraction equation. XA plus XB equal to 1. Okay, so you know XA, you should know XB. All right, same thing here. Same thing here. If you know YA, you should know YB. So just solve for YA, you will know your YB. Okay, so the feed here, F represent FA plus FB. Okay, the V here represent VA plus VB. Okay, and the L here represent LA plus LB. Okay, so that is what you have. All right, so F is also equal to V plus L. All right, so you learn about material balance already. All right, so it's easy for you to solve these questions. Okay, so bear in your mind, there are a few equations that you need to know. One is the overall mass balance. All right, overall mass balance. For your diagram, you can look for your schematic diagram. So input must be equal to output. Okay? All right. And then you focus on the mass balance of the more volatile component, the light component. All right. So what you have is F equal to XFA equal to, okay, so you have F multiplied by XFA equal to VYA plus LXA. So this star is for A only because this is the mass balance of the A component. Okay, so to simplify everything, okay, why do we need to have overall mass balance? So, okay, why do we have to know the overall mass balance and the mass balance of component A? I did mention to you, you have two unknowns. If you have two unknowns, you need to have at least two equations to solve the problem. Okay, so the equations can come from overall mass balance. The equation can also come from mass balance on more volatile component, which is A. You can also have mass balance on less volatile component, which is also B. Okay, so if you were to have all, meaning that you have three equations already. Okay, so you have more equations compared to your unknown. All right, it doesn't matter. So don't waste your time. All right, so you just use the number of equation as what you the minimum number of equations that you need to solve the problem. Okay, all right. So based on the equations that we have developed, okay, what we need is actually the operating line equation. Okay, the operating line equation. So you need to memorize this equation in the red color. Yeah, in the red color. How do we get this? All right. How do we get this? We have introduced to you. You can see that the symbol F here is introduced to you. Okay. What does it represent? This value of F represented by the value of vapor. Okay. The value of vapor divided by the value of the feed. Okay, so you can get it from here. Okay, how to get the small f? You just have to divide the amount of V with the amount of F. Vapor divided by the feed. Okay, all right. So by substituting this value of V over F, you get the term of F here to give you the operating line. So this is the operating of what? Flash or equilibrium distillation. So every condition that you're going to have a different operating line. Yeah? So this is what we call operating line. The term operating here represents the operating condition that you're going to follow for the process. If you have operating condition, the first operating condition, you're going to have the first operating line. If you have the second operating condition, you're going to have second operating line for your distillation. Okay. All right. So the term here represent, okay, it is looks like you have a linear equation with the intercept, okay, with the intercept of the graph, which is x over f, and the gradient of the graph, which is f minus 1 over f. Okay, so this is the techniques that you need to follow. Okay, very easy techniques. If you understand the technique, you can solve the problem easily. Okay, all right. First step. Okay, take a note. Okay, because you're going to refer to this all the time. You're going to refer to this in your quiz, in your assignment, in your final assessment also. Okay, first, draw a graph. Okay, why do we need to have this actually? Why do we need to have this? The purpose is to make sure that you're going to solve the equilibrium mole fraction that you have, the equilibrium mole fraction that you have. Okay, so what we're going to solve is actually to solve, if we go back to the diagram, okay, schematic diagram. In this subtopic, our purpose is to make sure that we solve Y star and X star, which is the equilibrium composition. The equilibrium composition for the given condition. Okay, so you're going to solve Y A star and X A star. So if you are given the first condition, maybe you would like to have YA1 star, XA1 star. Okay, if you given the second condition, you might want to present it as YA2 star and then XA2 star as your subscript. All right, the star here represent we have flash distillation, and this fraction, these components must be in equilibrium. Okay, let's go here. Okay, so our objective is to solve for this green value and this green symbol, Y star and X star. That is our purpose. Okay, so what is given to us normally? What is given in the questions? Okay, the given the data given in the questions normally is your equilibrium data. Okay, equilibrium data to give you the equilibrium curve. It doesn't matter whether the data is nice already and you just plot the data, or maybe you are the one who going to solve for X component and Y component, which is the vapor component and Y component, vapor component and liquid component XY at different temperature, as what we have done in the previous example. Okay, all right, so take a look at this. All right, so you draw the graph, you label the graph. Okay, so this is the mole fraction of vapor. This is the x-axis represent the mole fraction of the liquid. So you label the maximum value that you have, the domain that you have for x-axis is 1. The range that you have for the y value is also 1. Okay, and this graph must be big enough, okay, in your graph paper. Okay, so we're going to have a standard size of the drawing diagram that you're going to produce. Okay, all right. Next is, once you have labeled the coordinates, just connect all the coordinates and form a equilibrium curve. And the equilibrium curve must be smooth enough, okay, smooth enough, or at least meet the best fit line. Okay, best fit line. Okay, next is for you to draw the 45-degree line. So these are compulsory, yeah? Draw the equilibrium curve, draw the 45-degree line. Okay, why do you need to have that? Because it will easier to make our calculation drawing easier, okay, to get the final answer, right? So what data do you need? 1 is the equilibrium data. 2 is to know, okay, the information given in the question, which is what is the mole fraction of liquid at your feed? What is the mole fraction of component A in the feed stream? So you need to know that. So you just label, okay, label the fraction that you have for the A component at the feed stream, and then draw vertically until it meets the 45-degree line. Okay, so you need to have that line first. Second, All right, second, then what to do? Okay, next, you need to draw the red line. How to draw the red line? The red line is called the operating line. Operating line. Very easy to draw this operating line. You just write the equation of the operating line and go to the y-axis, y-intercept value that you have. Okay, how do you get that y-intercept? That y-intercept value is equal to xFA divided by f. Okay? xFA divided by f. So you know already how to get f. F is the amount of f, small f here, represent the fraction of the vapor over feet. Okay, so you get the value of y-intercept. So what you do, you need to do, find the y-intercept. Okay, let's say the y-intercept is about here. Okay, here. All right, it doesn't matter where is your y-intercept. Okay, so once you get this y-intercept, your job is just to connect that y-intercept value or coordinates to the intersection between xFA and the 45-degree line. So can you see this one? So this is xFA. You stop here at 45-degree line, and then you look for y-intercept and you draw the red line until it reaches the y-intercept. That's all. Okay. All right. So to answer the question, what is the equilibrium composition for this process? So the equilibrium composition of this process is y star and x star. Okay, where to get that y star, x star? You get it from the intersection between the equilibrium curve and the operating line that you have drawn. Okay, you just take the value of y to give you y star and the x value of x star here. Okay, to get the x star here. So that is the composition of the equilibrium composition for this particular process. Okay, so you get in terms of mole fraction. Okay, so that's all for flash distillation. All right. Okay, so you might want to try exercise 2. Okay, all right. So let me continue first. Okay, maybe you would like to try exercise 2. Can you? Okay, do you have the let's say heptane and octane? Hold on. Okay. All right, exercise number 2. You need to use the mole fraction that you get from X from the exercises. This one, exercise 1. Okay, exercise 1, where you calculate the calculate the alpha. Right? I've given you already, and you have made some sample on that. Okay, so I give you time to try. Okay, later how to draw this one. So you need to draw this one first. Okay, so please draw the equilibrium curve using this data. So this is heptane and octane. So using this data, okay, for X and Y, plot the equilibrium diagram. Okay, if you have the equilibrium diagram already, then it's fine. Okay, and then your job is to make sure that you answer the question using the method that we have discussed. Okay, all right. So what do we have here? Just read the questions. Later you're going to do these questions. A liquid mixture containing 70 mole percent heptane. So A, it is labeled as A. All right. So if it is not labeled as A, you should know that heptane should have lower boiling point compared to octane because of the number of carbon that you have. Okay, so this is liquid mixture containing 70 more % of heptane and 30 mole of octane at 30 degrees Celsius. So this is the amount of A that you have, right? So your XA should be equal to 0.7, yeah, 0.7. So you don't need to have this XB because you know it already, okay? No, don't waste your time, just write X. XFA 0.7. Okay, and to be continuously flash at a standard atmospheric pressure. Okay, so it's mentioned here continuously flash. So this is the keyword that you know this is a flash distillation process. Flash distillation process using flash distillation column. Okay. So at standard atmospheric pressure, okay, and vaporize 60 more % of the feed. Okay, vaporize 60 more % of the feed. So what will be the composition of the vapor and liquid and the temperature of the separator for an equilibrium stage? Okay, so you can do the estimation based on the data that you have previously. Okay, so develop at least 2 equations to solve the problem. All right, it comes from the material balance of overall material balance and the material balance for component A. Okay, and then you need to solve for the Y-intercept of the operating line. All right, Y-intercept of the operating line. And then draw the graph, okay, from the graph, okay, find the intercept between operating line with the equilibrium line, then you get the equilibrium composition of the vapor and the liquid, okay, so you can try to do that, okay. All right, any question? Close first. Any question? I give you time to ask questions. So quiet, eh? 62 only, and some are missing. Okay, now it's 11:15. All right, 11:15. I'm going to take another attendance. Okay, another attendance. So do you understand what's going on?
Yes, miss.
You
Clear.
understand? Clear? Okay. All right. All right. Now let's proceed to the second part. Do you need a break? No. You just run from the camera if you need a break. But I just want to let you know, because time to time maybe I will mention your name, okay? So if you were to go to the toilet ke, pergi mana ke, okay, you can just write some messages there that you are going to the toilet for a moment, so that I know that you were not in the class for a moment, but you have something to do. Okay, all right. So let's continue. Saya akan continue. You have question, please, please do ask question. Terlalu sunyi kelas ni. Maybe puasa takut tertidur je. Okay. All right. So I will continue on the fractional distillation. This is very important. Siapa yang mengantuk tu tolonglah basuh muka dulu. Siap-siap datang semula dekat sini. Saya bagi lebih kurang 1 minit sekejap. Sementara saya buat ni, prepare for this. You boleh pergi basuh muka sekejap. Because this is very, very important. Okay, very, very important. Okay, saya bagi 1 minit untuk you go and wash your face. Pergi minum tak boleh. Puasa. So this is very, very important for you, okay, for this topic, okay, which is called fractional continuous distillation or continuous distillation. Because majority of the questions or majority of the marks come from this particular section, okay, and I think it's about 20 marks, about 20 marks come from this part. Okay, so altogether you have 60 marks for your final assessment. 20 marks come from this part. Yeah. So you can see the distribution of the marks. All right. Okay. All right. Now, Bismillahirrahmanirrahim. We are in the second section. Okay. Continuous or fractional distillation column. Okay. All right. First, this is a schematic diagram. All right. So I'll show you later about the schematic diagram, the simplest one. All right. So what you need to know is to make sure that you know how to draw the schematic diagram actually. Okay, because it will give you some marks, sometimes 2 marks, 4 marks, just to produce the schematic diagram and label your schematic diagram. Okay. All right. What do you need to have in your schematic diagram? One is the column. Okay, the column that you have. Okay, so this is distillation column. All right. Next, what do you need to have? You need to have the output and the input stream. Okay? So the input stream is your feed and the output stream will be your distillate and the bottom product. Okay. All right. Distillate that you have in liquid form. Okay, before it is changed into liquid form, okay, it is in vapor form. Okay, in vapor form, condense, all right, and then you collect as a liquid, all right. So you're going to have vapor form on the top of the column, condense, and then you collect in liquid form. Some will be collected as your distillate product, and then some will be recycled back into the column, which is called reflux. Okay. Next, you're going to have bottom part of the column, which is bottom product. Okay. So what you can see is that some of your bottom product, all right, some of your bottom product will be recycled back into the column after it go through the reboiler. Okay, when it go through the reboiler, it will be reheat again. Okay, reheat again until it's formed vapor. Vapor will be rise again until it reach the top of the column. Only the light component will reach the top of the column. The heavy component or heavier component may be vaporized first, but it will turn back into liquid because it is heavy. When it reaches to the top of the column, it's become heavier and turn back into liquid form and go down the column again and again. So this process occurs again and again. The lighter component, which go through the reboiler, will be vaporized. Okay, when it's vaporized, all right, maybe some of them consist of some of them still, some of them may be still heavier, so it will turn back into the liquid form, turn to the bottom of the column. But the lightest component will keep on rising to the top of the column, okay, and collected at the top of the column Before that, it will be condensed and then turned into liquid form. If you want to collect the product, you just open the valve and collect the product. And if you don't want to have the product, you can reflux back into the column. So whatever decision that you have made, you're going to make in this part, will always refer to the quality of the product of distillate that you would like to have. Okay, if it doesn't meet the purity of light component that you would like to have here, you can just reflux back into the column. Okay, so when it's reflux back into the column, you can see the contact is between the vapor and the liquid will occur again and again. So what you can see here is actually to have a good separation. Okay, there's a theory of mass transfer that you need to know. Mass transfer that you need to know. That is between gas and the liquid. The gas goes up, the liquid goes down. So there will be a contact between the gas and the liquid. Okay, and the transfer of the mass will occur only at the thin film between the vapor and the gas, or the surface area between the vapor and the gas. Okay, so that thin film we need to have in order to get a good separation or good mass transfer. So that's why you need to have a contact area, which is a very big contact area, okay, between the vapor and the gas, between the vapor and the liquid, sorry. Okay, so that is basically on the schematic diagram of the fractionating distillation column. So what do you have? You need to have a column, you need to have input stream and output stream. Okay, that's all. Okay, to give you the distillate or not. Okay, but if the question consists of a reflux ratio, so you need to produce, at least show the condenser, okay, and the reboiler. Okay, there are a few exceptional lah for you to have the schematic diagram. Okay, so I'm going to show you some examples after this. Okay, so we're going to have a multi-stage fractional distillation column. Okay, so for this purpose, okay, like what you have learned in the first section just now, which is flash distillation column, where you are given the operating line. You are introduced with the operating line of flash distillation column. Okay, so you can remember back the flow for flash again. Okay, for flash, what do you have? Okay, for flash, you need to have equilibrium data, you need to have equilibrium curve, you need to have 45-degree line, you need to have operating line. So once you have 45-degree line, equilibrium curve, and you have the operating line, you can solve the equilibrium composition of your flash distillation column. Flash distillation process. Okay, but for the fractional or continuous distillation, okay, so you're going to have distillate, okay, and you're going to have bottom product also. Okay, so because of that, you need two operating condition, operating line, two operating line, not two operating condition. You need two operating line. The line come from enriching section and stripping section. So ada two operating lines. Okay, all right. So this is just to simplify the schematic diagram. So draw the schematic diagram, draw the feed stream, you draw the bottom product, you draw the reboiler, and then you have the stream that goes into the column again, and then you have the top product, you collect your distillate here, and then you reflux some of your top product into the column again until it reach the purity. Maybe you would like to have the purity of your distillate 90%, 95% of your A component. Okay, so you decide once you get that purity that you would like to have, then you can close this one, this valve, and then collect your distillate here. So your distillate normally consists of majority of your A component or light component. And at the bottom product, you're going to collect majority of the heavier component or your heavy component lah. So again, heat energy will be provided in the process. So that's why distillation process is expensive. Okay, expensive. All right. And then again, the temperature that you're going to have, you have lower temperature at the bottom of the column. High temperature at the bottom of the column and lower temperature at the top of the column. So that is the distribution of the temperature that you have in the column. Higher temperature at the bottom, lower temperature at the top. Okay. How much distillate that you get? You are trying your best to get the highest composition of A components at your distillate. Why distillate consists of majority of component A? Because A component has lower boiling point compared to B component. Okay, all right. So we are talking about the equilibrium composition here also. Okay, so you can read how does it happen in the process. Okay, so you have to know that whenever that we have feed, okay, feed, you have the feed stream, okay, and you're going to feed the mixture in the column. Okay, the tray above the feed tray will be categorized as enriching section. Okay, the tray below the feed tray, okay, will be considered as stripping section. So you have enriching section on the top of the feed stream. Sorry. And stripping section at the bottom of the feed stream. Okay, so at the top of the feed stream, you're going to have enriching operating line, and at the bottom of the feed stream, you're going to have stripping operating line. Okay, so the feed. Okay, the feed has different condition. Okay, very important here. Okay, if you are given the condition of the feed, you're going to have another operating condition. You're going to have another operating line. Okay, so if you are not given the condition of the feed, you're going to have only two operating line: enriching operating line and the stripping operating line. Okay, that's it. Close the case. And then you start do the calculation. But if you're given the condition of the feed, you're going to have three operating line. Okay, that operating line should include Q operating line. Q operating line. Okay, so what is the condition of the feed? Okay, there are many. You have to read the question properly whether it is mentioned about the feed condition or not. Okay, for example, it will say the feed consists of liquid only. Okay, ataupun the feed consists of saturated liquid. The feed consists of liquid at boiling point. Okay, the feed consists of a mixture of liquid and gas. Okay, the feed is totally vapor. So that is called the condition of the feed. Okay, something like that. All right. So make sure that you read the question properly. Okay. Next. So you can read how it works. Okay, you can read this part and then you can read the textbook also. Okay. So we have, in order to solve the problem, what to solve actually? What to solve? We are actually wants to solve the mole fraction of the distillate and the mole fraction of the bottom together with the together with the flow rates of your distillate and flow rates of your bottom part. Okay, total flow rates of your distillate, total flow rates of your bottom product. Okay, so this is a total flow rates. Total flow rates of feed equal to total flow rates of distillate plus total flow rates of bottom. Okay, so we are using D and B. So no more L and V. Okay, L and V is used for flash distillation. Okay, so to easily understand what's going on in the equations, okay, so mass balance on component A will be used. Okay, so this is binary. So you're going to have Fx Fa equal to Dx DA plus Bx Ba. Okay, to represent the component A. Okay, so these are the assumptions that we need to do. Okay, column operates at steady state condition, and we assume constant molar overflow in the column so that we can use this equation. Okay, all right, so just to simplify, so that's easy for you to solve the problem. Okay, so this is the first section, how we're going to solve the enriching operating line. Yeah, enriching operating line at the enriching section. So you need to have enriching operating line first. Next, you need to have a stripping operating line. Maybe you would like to have Q operating line. Okay, so one by one, eh? Okay, now, so because an enriching section consists of the top of the column, so you're going to deal with the distillate. Okay, you're going to deal with distillate. All right, so you are dealing with the top of the column. All right, so to make it simple, you need to have some information regarding to your distillate composition of less volatile component. So you need to have XDA. Okay, you need to have XDA. All right. Why? Okay, so let's look at this. All right, XDA. All right. So this is the enriching, how enriching operating line is developed, and this the second one, equation 13, will be your enriching operating line. Enriching operating line. So you need to memorize this one. You need to understand this enriching operating line. So look at the equation. Okay. So you have XDA. Here you have X. Okay. You have also R. Okay. R is the reflux ratio. It's a value. Okay. How do you get reflux ratio? Reflux ratio is obtained from Ln over D. Ln over D. Where do you get Ln in this case? We know that from the schematic diagram that you have, okay, schematic diagram that you have, you can refer to this small section, the schematic diagram, the top of the column, okay, you have the vapor at the top of the column, condensed, it becomes liquid, okay, and some will be collected as your distillate, some will be refluxed into the column. Okay, so the symbol that you have is distillate is D. Reflux, for this one, reflux is L. So in this equation, Ln represent this L. Okay, Ln is this L. So it's easy to say that, okay, this stream is called D. And that stream is called Ln. Okay, Ln. Okay, all right. So make a short notes on this lecture so that it's easy for you to look through this concept. Okay, so you have D and Ln. All right. So where the top product will be split into two streams. Okay. So look again. Okay. Reflux ratio means the ratio of the reflux flow divided by distillate flow. Okay, to give you reflux ratio. Okay, so in order for you to solve for enriching operating line, there are two things that you need to solve. One is the mole fraction of your distillate for component A and the reflux ratio for the distillation column. Okay, you need to have two things here to solve for your operating line. Okay, so you need to have that information. How to get that information? There are two ways. One is from your understanding on the questions that you get the information of the reflux ratio. Second is from the solving the equation. Okay, you get the reflux ratio. Okay, so by looking at this, you're going to have a straight line form. A straight line form. This is your gradient. Okay, and this is your Y-intercept. Y-intercept. Okay, all right. So how to draw? Okay, follow Okay, so sketch dulu. All right, sketch sketch. Okay, so this is stripping nanti dulu. This one, sorry. Okay, so you need to sketch the curve. You need to sketch the curve. All right, equilibrium curve. Yeah. So draw dekat you punya kertas, buat vapor exists, vapor fraction exists, and then liquid fraction exists, mole fraction. Okay, just draw the equilibrium curve until it reach this particular position, which is at the end of the curve, at the end of the at the end of the value of vapor and liquid. Just produce a curve, draw a 45-degree line, okay, which connect between 0, 0 and 1, 1. Okay, all right, and then assume the value of your XD. Just assume somewhere here. Just sketch. Don't draw the graph. You draw your XD. Okay, so label your XD and then draw the vertical line to the top of the column, to the top of the graph. Okay, stop when you reach the 45-degree line. Stop there. Okay, stop there. All right, and then you need to have the Y-intercept of your enriching operating line. Okay, so that is the equation of the Y-intercept of an enriching operating line. So let's assume this is the point of the enriching operating line after you substitute the value of XdA over reflux plus 1, R plus 1. So you get this intercept. And then what you need to do is to connect the intercept to this 45-degree line where it meets the XD. Okay, all right. So this dotted line is called enriching operating line. So normally we just use EOL. Okay, EOL. All right. So when you have this enriching operating line, okay, without fit condition, you just continue. Okay, without fit condition, just continue. where you need another information of your stripping operating line. Okay, so the stages that you need to calculate, you need to draw is this stage lah, on the top of this particular enriching operating line. So why do we need to know the to draw these particular stages? Okay, so when you go back to the questions, all right, to the theory, when it's involved the continuous or fractional distillation column, it's involved many stages in front, or what we call multiple stages. Okay, for flash distillation, number of stage is only one. Okay, one only, one, where you have the feed and then you separate vapor and liquid. So we consider as one stage only. For fractional and continuous distillation, the difference are the number of stages. Here you have multiple stages. Okay, so number of stages is considered as one important parameter for you to design the distillation column. Okay, number of stages. So this involves design also. Okay, design. Okay, so maybe in the case that you would like to separate the mixture, that you have. Okay, first you need to check the alpha. Possible or not possible to use distillation process. Okay, all right, let's say it is possible to use this process. Next thing for you to do is to make sure that the number of stages here is enough, okay, for you to proceed the process. Okay, number of stages here is enough for you to proceed the process with the quality that you would like to have for your product. Okay, whether it is distillate or your bottom product. Okay, all right. Oops, baliklah pula. Okay, sorry. Actually, I want to zoom. Okay. All right. So that's the need to know the number of stages. Okay. Right. But to know the design, to know the number of stages needed, okay, sometimes because you know what kind of quality of product that you would like to have. Okay, you know the quality. But what's available sometimes in the industry, okay, what's available, because sometimes when you go to the industry, the distillation is there already. Okay, and let's say the number of stages that you have for that particular industry, let's say 30 stages. Okay, 30 stages or 30 trays. All right, 30 trays. 30 trays. Okay. So you would like to know whether it is possible to have the quality of your distillate with the number of stages available for that particular equipment. So you can do the calculation, which is to determine the number of stages. Okay. So after you do the calculation, let's say you just need about 20 stages. But in the industry, you have more than 20 stages. In that particular industry, factory ke, okay, plant ke, okay, you have 30 stages over there. But what you need is 20. Okay, so proceed because you have more than what you need. Okay, more than you need. Okay, but if you do the calculation, you need more than 30 stages. Okay, but what's in the company, you only have 30 stages. Let's say you need 33 stages. But in the industry, that you have, they have only 30 stages for the equipment, for distillation column. All right. So, what do you think? Do you want to proceed or not? Think about it. The distillation column is very expensive. It's not just easy to, okay, I need 35 stages, but what we have in this industry, we only have 30 stages. So let's buy a new distillation column. No, it will not happen that way. Okay, so normally the asset remains in the industry maybe more than 10 years, 20 years. Okay, it's not that easy. Okay, so what do you need to do? You need to use whatever available equipment that you have in front of you. Okay, so you need to change some parameter, input parameter before you proceed. Okay, so you need to have some changes. Okay, what changes that you can do? The only changes, easy changes that you can do is to change the condition of the feed. Okay, to change the condition of the feed. Okay, that is one option. So because you need to change the condition of the feed, that will affect the number of stages that you have in the column. Okay, so whether you want to reheat first the feed, maybe you would like to have the feed in liquid form, whether you want to have the feed in vapor form, whether you want to have the feed in a liquid and mixture form. Okay, so you can do that assumption first and then calculate. Okay, calculate what? Calculate the purity of your distillate. Okay, so what else can you do? This is what you can control. Okay, what you can control, right? Next thing you can control is the reflux ratio. Reflux ratio. Okay, so you can change the reflux ratio because you can change the amount of distillate that you would like to collect. You can change the amount of reflux that you would like to feed into the column again. So that's your choice. You can control that. So by changing the reflux ratio, you can also change the purity of your distillate. Okay, you can also change the number of trays that you have in the column, the number of stages that you have in the column, so that it will meet the requirement or the whatever that you have in the industry. Okay, so this is the decision making that you have to do. As a chemical engineers, you are to design the process, you are to design the equipment. Okay, all right, so that's your job. Okay, so maybe part of it is as a decision maker. Okay, so that's why it is very important for you to know the number of stages. So the objective is to calculate the number of stages. Okay, so this is the theoretical graphical method to calculate the number of stages. Okay, all right. Next is about equation for stripping section. I will go fast because under stripping section, all right, so it's not that easy to draw the stripping operating line. So the symbol that we use is SOL, stripping section. Okay, stripping line. Okay, so how do you get that? So you're going to focus for stripping section, you're going to focus at the bottom of the column. Okay, you're going to focus at the bottom of the column. So because you're going to focus at the bottom of the column, from the graph that you're going to draw, so you have to label XBA. Okay, XBA. So remember again, everything is about A. Everything is about a more volatile component. Okay, XBA. B here represent bottom lah, not component B. Okay, so you have XBA. Okay, so XBA must be known here. So same thing as what you have done for XDA. You also have to draw the vertical line until it reach. You stop until it reach the 45-degree line. Just stop here. Okay, stop here. So if you were to begin from here, okay, so you need to know the slope. Okay, so you need to know the slope. The Y-intercept does not play easier way to solve the problem or to draw the SOL. Okay, so you need to know the slope. Okay, so once you know the position of XBA, okay, here at this position, all right, So the next thing is for you to know the gradient of the slope. Okay, so you have to begin to draw the triangle starting here. So you need to know how do you calculate the gradient? It should be the delta y divided by delta x, right? Okay, so you might need to know, okay, the highest length for your triangle and the base length of your right angle triangle, okay, to get the gradient. All right, so look at this. Okay, so this is how you get the gradient, yeah, for the stripping operating line. So the gradient is L over V, L over V, and this part is your Y-intercept. Okay, so we just need L over V. What is L? What is V? Okay, L is the amount of flow rates of the liquid, and V is the amount of the vapor. Okay, so that you can get the slope of L over V. All right, so L, so if the information given to you for the liquid and vapor, you just calculate the ratio, okay, and then substitute and then calculate the value to get the gradient. Okay, so let's say the gradient that you have here is, let's say 2 or 2.5. It doesn't matter. I make it easy. Let's say the gradient that you have here is 2. Okay, all right, so 2. How do you get 2? So you just draw, get 2 units, get 1 unit at the bottom, because 2 is delta y over delta x. 2 is delta y over delta x. M is equal to delta y over delta x. So 2 means 2 over 1. 2 over 1. Meaning that 1 part of x and then 2 parts of y. Okay? So you just calculate from here to here. Let's say you're going to use that as, so let's say 0.4. Let's say here is 0.1. So you have 3. Okay? 0.1, 0.2, 0.3, 0.4. Okay, so you have 3 parts down here. Okay, 3 parts down here. Okay, so because you need to have 2, so you need to have your height to be 6. So you go to the top 6. Okay, 6 unit. 6 unit to the top, and then 3 units at the base of your right angle triangle. So once you get the position here, okay, so you just connect the line. Okay, connect the coordinates. So you produce the stripping operating line. Okay, all right, so I will explain more based on the example later. Okay, today I have to finish up to the Q operating line. Yeah, so that's our objective. Okay, so once you settle with stripping operating line, okay, so we're going to look at the effects of feed condition. I mentioned to you this already. So if you're given the feed condition, so the feed condition can be liquid, the feed can be in liquid form, the feed can be vapor form, the feed can be a mixture of vapor and liquid. Okay, so that are called the feed condition. Okay, all right, so what to do? Okay, the effects of feed condition will give you extra operating line. That extra operating line is called Q operating line. Okay, Q operating line. Okay. All right, guys, do you have any question? Semua sedang mencerap, eh? Saya doa semua sedang mencerap hari ini. Okay, so this chapter is not difficult. Once you know how to solve the technical part, then your calculation part comes next. Okay, so technical parts is very important. So this is graphical method. All right. Okay, so you need to know how to calculate the basic method, which is graphical method. There are many methods actually. Many methods can be used to solve the problem. Okay, one is called the graphical method. Okay, but if you work in the industry, okay, maybe they are not going to use the graphical method because they have the software already. Okay, they have the simulation software already. You just plug in the value, make some assumption, and then get the forecast result. Okay, so you can do the simulation on the process. So that one is shortcut lah, right? Biasa lah kan. So if you were to learn this one first time, it's kind of difficult, but that will give you the good memory lah, the good theory, the good information where you can keep to your mind. You can use your experience in future. Alright. So macam you mula-mula belajar berjalan lah kan. Kan susah nak belajar berjalan ni masa baby kan. So you kena jalan-jalan sikit jatuh, jalan pegang tepi, pegang kiri, pegang kanan kan. So that experience will give you information. Alright, you need to stabilize yourself, okay, so that you can walk straight. Okay, so bila you dah dewasa, dah tak belajar dah cara berjalan, tak belajar dah. Unless you have a new information, new theory, you want to apply to the method of you walking. Nak jalan macam rat ke, that is new information. Susah nak jalan macam rappers ke? Rappers boleh panggil. Okay, so itu semua new information. Okay, so this is the first time you learn the distillation, do the calculation. Okay, kind of a little bit difficult, but it will develop the theory, your understanding better in future. Okay, so what is important here? All right, Q operating line. If you were to have final exam, you need to memorize. Okay, but now for this particular semester, okay, you're going to have online final assessment. Okay, so you can refer to your books, so you don't need to memorize. Okay, so the equation is y equal to q over q minus 1, x minus xf over q minus 1. What is xf? Okay, xf, okay, take note, take note. Every time I mention about operating line, you have to take notes. You have to take notes on what I have mentioned here, okay, so that you understand the next step. Okay. Q operating line developed because you have feed condition. So because you have feed condition, all right, so look at the y-intercept. The y-intercept consists of negative sign, negative sign. The y-intercept is equal to negative xf. It must be xfa over q minus 1. xfa. You are given the condition of the feed. So the y-intercept involves xfa. Sorry. Okay. Feed condition, Q operating line involve xfa. Okay, now go back. All right. If you go for enriching operating line, it's involved the enriching section. Therefore, it's involved the distillate. So you use XD. And then it's involved the ratio or the reflux that you're talking about. Okay? You have to remember, you have to know what is reflux. Reflux is the flow rates of L and divide by D. Okay, all right. Now, stripping is not that really important. It just go with the flow. But what is important is the gradient. Okay, the gradient. Okay, I mentioned that already. Okay, now here you are given the feed for Q operating line because it's involved the feed condition. Do not confuse with the mole fraction of the feed, mole fraction of the distillate. Okay, now what is the value of Q? The value of Q, right, represent, okay, this particular condition and that particular condition. Okay, so if your feed is in superheated vapor, the value of Q must be less than 0. It should be negative value. Okay, negative values. All right. Okay, maybe your feed is saturated vapor. If your feed is saturated vapor, the value of Q is equal to 0. If you are given the feed is a mixture of liquid and vapor, the value of Q must be between 0 and 1. Okay. If you are given your feed is saturated liquid, the value of Q is equal to 1. But if it's cold liquid, the value of Q should be greater than 1. So this is your guidance on the value of the Q. Okay. What is specific here? The specific part is when it is at saturated vapor and at saturated liquid, because the value is fixed, which is Q equal to 0 for saturated vapor, Q equal to 1 for saturated liquid. How does Q equal to 1 looks like? How does Q equal to 0 looks like? Okay, again. So I give you the information and the comparison, yeah? Okay. Now, you draw the Q operating line. Only one lah. One Q operating line. Okay. If your feed is saturated vapor, your Q is equal to 0. Q equal to 0 is the horizontal line. Okay. But if your feed is saturated liquid, you're going to have vertical operating line. Okay. Now the question is, where do you begin to draw the operating line? Remember? Okay. So now let's revise a little bit. Okay. So Q operating line begins at the 45-degree line, where this 45-degree line intersect with, okay, you need to draw XFA. Yeah? XFA at the bottom, draw the vertical line until it's intercept the 45-degree line. If it is saturated vapor, you just draw vertical line at this particular point. Okay. If it's saturated liquid, you just draw the vertical line. Okay. So you have vertical line and horizontal line intercept with the intersection between 45-degree line and your XFA. Yeah. So they are very relevant. They have the connection between what you are mentioning in the questions. Okay. The feed condition, you use XFA. You begin to draw your operating line at the intercept of XFA with 45-degree line here. Now let's go to this one, enriching operating line. So if you were to draw the enriching operating line, okay, it's begin at your distillate. Okay, so let's look again. XDA. So this is where you draw the XDA. Draw vertical line until it's intercept 45-degree line. Okay, then you begin to draw your enriching operating line. Okay, and make sure that you know the y-intercept of the enriching operating line. They have the same pattern actually, same pattern. Okay, same pattern for you to solve the problem. Now, if you are looking for the bottom, you begin at the XBA. Okay, and then you draw the stripping operating line. Okay, so that's the similarity of the method and the difference between SOL, EOL, and QOL. Okay. Sorry. Okay, there is another method that you can use to calculate. Take note, now you take a note. Okay, take a note, right? What if the fit condition given to you mention about it is a mixture of liquid and vapor? The value is between 0 and 1. Okay, 0 and 1. Okay, all right, 0 and 1. Okay, so how do you get the values? Okay, it comes from the equation, it comes from the questions actually, come from the questions, all right? So you're going to multiply, if you were to use this one, okay, actually there are many methods of calculating this part, okay? So you must be given how much liquid and how much vapor that you have in your feed. How much vapor, how much liquid that you have in your feed. So maybe your feed consists of 40% liquid and therefore 60% vapor. 40% liquid and 60% vapor. Okay, all right. So if you were to have 40% liquid, okay, so the value of Q, okay, take note now. Kenalah take note kan? Okay, take note now. Okay, so your value of Q should be, take a look here. Saturated liquid, the value of Q is 1 and the vapor is 0. So it's easy to look at the value of Q is equal to, all right, 0.4, okay, because 40% liquid, 0.4 multiplied by 1, okay, because it's liquid and liquid, right? 0.4% liquid and 60% vapor. So 0.4 multiplied by 1, okay, so you get 0.4. So it's slice less than 1, okay. But if in the question give you that it just mentioned only 1, not to mention the liquid, but it's mentioned about the vapor. So it just gives you the reverse calculation. Okay. So if the questions give you 60% vapor, okay, therefore automatically you should know the 40%, the balance 40% represent liquid. So you just do the same thing, which is 0.4 multiplied by 1. Okay, so that is how you get the value for the Q. Okay, so if you have this condition, okay, this part, okay, then you need to use Q operating line. Okay, Q operating line. You need to calculate manually the Q operating line. But if you were to use Q equal to 1 or Q equal to 0, you don't need to use this equation. Just remember that at Q equal to 0, it must be a horizontal line starting at XF. If Q equal to 1, you just draw a vertical line starting at XF. That's all. All right, that's all. But if it's the value between 0 and 1, please use this equation. Okay, so you need to know the y-intercept only. So do not bother about the thing because you know where it's begin. Okay, so just use xf. Just now we have 0.4 multiplied by 1. So you just use the y-intercept for the q operating line is negative xf over q minus 1, which is negative xf divided by 0.4 minus 1. So you get the value of y-intercept. Same method as what you have for the enriching operating line. So let's say what you get is maybe more than 1. So you just take the point there, more than 1, y-intercept, and then connect to the interception that you have known already. Okay, if you have the y-intercept equal to 0.8, so you just take 0.8 here, draw the straight line until it meets xf at the 45-degree line. Okay, so basically this is what you have to do. Okay, all right. Okay, so we only have this one. I will explain to you later. Okay, there are many types of reflux. Okay, so there are three types of reflux actually. Okay, one is called total reflux, another one is called minimum reflux, and the last one is optimum reflux. Okay, so this is how it looks like. So you're going to draw your XD. If you were to have total reflux, okay, what you need is only XB and XD. You don't need the XF. Okay? In this one, it uses ZF. Okay? It's okay, but this is XF actually. So XD, XF, XD, XB. For total reflux, so you just draw the stages, the number of stages starting from XD until it reach 45-degree line, and then draw vertical line until it reach, draw the horizontal line until it reach equilibrium, and then draw the vertical line again, and then horizontal line, and then vertical line. So you stop until it reach one step further than XB. So you stop. If you want to draw again, it doesn't matter, but you stop here. Okay, you stop here. All right, because it reached more than XB already here. Okay, so this is total reflux. Okay, but if you were to have a minimum reflux, okay, the name given is minimum reflux. So you need to have EOL. So this is EOL, and then you need to have SOL. Okay, all right, and maybe you need the QOL. All right, so if you were to have minimum reflux, okay, it's enough to have 2 operating line. Enough, eh? 2 operating line. Okay, it doesn't matter whether you're given the condition of the feed or not. Okay, but what you need is at least 2 operating line. Okay, at least 2 operating line. But what if you only have 1 operating line? Also can. The minimum reflux, okay, need at least 1 operating line. Senang kita. Tak perlu 2, tak perlu 3. Minimum reflux. If you have enriching operating line, you just draw enriching operating line. The moment it touches the equilibrium curve, that is called pinch point. Okay, so the pinch point is the common interception. So automatically you can draw your Q operating line starting from XF and then just meet the pinch point. And then you can draw your XB, just meet at the pinch point. So you get how the minimum reflux looks like. Okay, so if you look again, if you just have SOL, enough. You just extend the line until it reaches equilibrium line, So that point is called pinch point also. And then you draw the, from XD, you just bring along your EOL. From XF, you can bring along your QOL. Or you can just have QOL because you are given the fit condition and you don't know the information, you don't have the information for EOL or SOL. You just draw the QOL. So when it touches the pinch point, then the rest will follow. Okay, so if you compare both, a number of stages for total reflux means that everything will be fit into the column again. No distillate will be collected. Okay, that is total reflux. Everything will be fit into the column, meaning that you close the valve for XD, but you open for LN. Okay, so the number of stages you need is minimum. Okay, minimum. So you can see here about 1, 2, 3. Okay, here you have more. Okay, now theoretical stages that you need. Okay, you have to make sure before you calculate the number of theoretical stages, you have to deduct by 1. Okay, deduct 1. Okay, I mention that because this is theory, maybe it doesn't mention. Okay, it doesn't mention. So number of theoretical stages for this case for total reflux is you just label 1, 2, 3. Okay, so this is doesn't reach 3 actually because the steps is less than 3. So you have step 1, step 2, step 3. Okay, so the number of tray that you have 1, 2, 2 point something. Let's say 2.8. Okay, 2.8. All right, 2.8. All right. So if you were to have 2.8, okay, the number of theoretical stages should be 2.8 minus 1, which is 1.8. Okay, so that is how you calculate. All right. Okay, so when you have these things, all right, so you have to make sure that you know how to calculate. So I will give you some video on the tutorial question number 1 and number 3. Okay, please read, please watch the video, the method how to solve the questions relating to the continuous distillation. Okay, so that you have some understanding on how to solve the problem. Okay, all right. So I think that's all for today. So I will attach the video here, okay, down here. All right, and then what you need is to watch the video. Just click here, down here, after the mass lecture class. Okay, so please spend time to watch the video before you go for your tutorial session. Okay, all right. So is there any question that you would like to ask? Ada soalan? No. Ya, student ada 70 lebih tapi seorang je bercakap kan. Sedihnya saya.
Ada.
Tak ada. Okay, saya harap so faham. I will give you the link to the video. Jangan leave lagi ya. Siapa share ni? Siapa nak collaborate tu? Okay, hold on. I will take the attendance for today. Do not leave the meeting yet. Okay, so I put the link for the YouTube video. That's my explanation on some examples, and you can read that and you can watch that video. Okay. All right. Thank you very much. See you in the next class. Assalamualaikum.
Thank you, Miss.
You're welcome.
Thank you, Miss.
Thank
you, Miss.
Thank you, Miss. Thank you, Miss.
You're welcome.